So today we are going to discuss about the bridges. So this comes under module 4 under power electronics and instrumentation. So we were discussing different type of instruments which we use to measure the different parameters. Okay. To name a few, we have discussed about the digital voltmeters, digital multimeters, frequency meters and the measurement of time, right, by using different techniques. Okay, we have seen that how the various parameters in the laboratory, whatever the devices we use, okay, how it is going to work and how the different parameters like voltage, current, frequency can be measured, is it not? So, here in today's class, now so far we discussed about an voltage, how to measure the voltage, how to measure the current, these are the sources, isn't it? So, in today's class we are going to see how we are going to measure the load elements. So, which are the load elements which we know? We know that the load elements are, which are they? The resistor, L and C, R, L and C. So, resistors, inductors and capacitors, isn't it? So, to measure this components, the load elements, that is the resistors, inductance and capacitance, we make use of something known as bridges. Okay. So, bridges means, to say in its simplest form, it consists of a, let us say for example a resistor. So, it consists of 4 different resistors connected with a voltage supply. It can either be a DC or an AC source as well as a galvanometer or a detector. Okay, either to find out the presence of current, you make use of a galvanometer. So, this is the simplest form of expressing a bridge circuit. Okay. So, in detail if you want to go to measure the resistance. Okay. So, today's class we will study the measurement of resistance. Okay. To measure the resistance, the most accurately used method is the Wheatstones Bridge. So, this is the method by making use of Wheatstones Bridge. As soon as I say Wheatstones Bridge, you will get an idea of a square shape where you have 4 arms with resistors and 2 resistors are already fixed. The third one is a variable. You have to determine the unknown quantity. That is what comes into picture when we say Wheatstones Bridge, isn't it? In between the bridges, in between the arms of the bridges, what we have? We have a detector. Here we are going to make use of, in case of Wheatstones Bridge, we are going to make use of a galvanometer which is going to detect the presence of current. So, if one arm of the bridge is having the current flow, the detector detects in the deflection points in one direction. If the other arm is going to have a current flow, so what happens? This detector galvanometer deflects in the opposite direction. When all the 4 arms are in a balanced condition, then what happens? Detector, there is no current flowing, so detector points 0 in between. Okay, so this is how, by making use of a galvanometer, we are going to measure the unknown resistance. So, as I said, out of the instruments whatever we have studied so far, okay, voltmeters, multimeters, frequency meters, time measurements. So, these bridges are specifically used to determine the value of the unknown load elements. Okay, starting with the resistors. So, for the measurement of resistance, the widely used bridge is the Wheatstones Bridge. So, as soon as I say Wheatstones Bridge, we all know that. So, let me draw the figure. We are going to draw the figure for a DC Wheatstones Bridge, where we are going to make use of a DC supply as the input. Okay, it should consist of how many resistors we know? It is having 4 arms. Okay. So, 4 arms. To find out the unknown resistance, this is the most accurate method what we are going to use. Okay, let us say we are going to place a galvanometer current detector in between these 2 arms. Okay. So this is the DC input with positive and negative terminals. This is the R1, R2, R3 and R4. Usually R1, R2 are fixed value of resistors, R3 will always be a variable one, okay. And R4, at the arm R4, usually we are going to connect the unknown value of resistance. So by varying this, okay, we cannot vary this, it is fixed. By varying the value of the resistor R3 accurately, okay, accuracy is very high compared with the respect to the Wheatstones bridge, okay. So the accuracy is so high that we can easily determine the value of the unknown resistance, okay. Now let us say this is the total current flowing in the circuit. Now let us say the current is getting divided into the branch I1 and I2. Now this current that is getting divided here has to meet at this point again. So let us say with respect to the R3 arm we have the current I3 flowing, with respect to the R4 arm we have the current I4 flowing. So at this point what is happening, if this is the total current flowing here, okay, it is going to get branched to I1 and I2 with respect to R1 and R2 resistors. Similarly, at this point let us say the Wheatstones bridge, I3 and I4 are the currents that is flowing through R3 and R4 respectively, which meet at this point and we are going to get back the same current. Now, can we write I1 into R1 is equal to I2 into R2? Okay, since we know that it is a balanced condition. Let us say A, B, C, D are the points that we are going to use in the case of the Wheatstones bridge, okay. Now to say that the bridge is balanced, what we should say, to obtain the balanced condition for a bridge, we have to write this value, this arm should be equal to this arm, yes or no. So what we are going, I1 into R1 should be equal to I2 into R2, okay. Let us call this as the DC voltage supply, Vs or V. Now see the circuit, when the galvanometer now, if the arm, that is if the current is deflecting in one direction, if the current is flowing in one direction, then it is deflecting to one end of the galvanometer. If it is deflecting in the other arm, it goes to the deflection in the other arm, okay. When it is balanced, this is for to obtain a balanced condition, okay. Now let us consider that the galvanometer current is 0. So the current flowing through galvanometer, assuming it to be 0, if this is 0, okay, what will happen? The current flowing through I1 will be the current flowing through I3. Do you agree with that? If this is 0, I1 current is the same current flowing to I3 and it is coming to the back to the supply. Similarly, I2 current flowing here is same as I4 current going back to the supply. So can we write, when the current, galvanometer current is equal to, okay, the current flowing through the galvanometer is 0, then when the galvanometer current is going to be 0, the following conditions have to be satisfied. So what are they? The current I1 in of the bridge R1 and the current of the arm R3 must be equal. Yes, it should be the same current. Similarly, current I2 must be equal to current I4. Okay. So now what is the equation for current I1 we wrote? So I1 that is equal to I3 is equal to, what will be the total voltage now? V divided by, see the circuit, R1 plus R3. V by R1 plus R3 will give you the total current flowing. Yes or no? We are going to write V divided by R1 plus R3. Okay, this branch. So when this galvanometer current is equal to 0, R1 plus R3, which is the sum of the resistors, V divided by the sum of the resistors will give the total current flowing, which is nothing but I. Okay. Similarly, when the other arm of the bridge we have R2 and R4. Okay. So, R2 should be equal, that is I2 will be equal to I4 means what will happen to the voltage? This arm, okay, R2 plus R4, whatever the resistance we add, when we divide that, V divided by R2 plus R4, we are going to get back the current I2. So, for this, when I2 is equal to I4, we are going to get R2 plus R4. Okay. So, now you can see that if the condition of the galvanometer has to be satisfied, that it should be 0, then I1 should be equal to I3 and I2 should be equal to I4. Okay. Let us call these equations as this as equation number 1, equation number 2 and equation number 3. Now, I1 into R1, we know that if the bridge has to be balanced, this arm should be equal to this arm. So, I1 into R1 should be equal to I2 into R2 to be balanced bridge. Okay. So, now to maintain the conditions in balance, these are the currents that has to be following this pattern. Okay. So, now what we are going to do, can we substitute I1 as equal to V by R1 plus R3 and I2 as V by R2 plus R4. Okay. So, substituting equation 2 and 3 in equation 1. So, substituting equation 2 and 3 in equation 1. Okay, substituting 2 and 3 in equation 1, what we are going to get now? I1 into R1. So, I1, instead of I1, can we write V divided by R1 plus R3 into R1, that is equal to V divided by R2 plus R4 into R2. Yes, can we write it like this? Substituting in equation I1 into R1 is equal to I2 into R2. So, what we are going to write? V and V will get cancelled. So, R1 by R1 plus R3 is equal to R2 by R2 plus R4. Cross multiply R1 into R2 plus R4 is equal to R2 into R1 plus R3. Fine. Cross multiply and write now R1 into R2 plus R1 into R4 is equal to R1 into R2 plus R2 into R3. R1, R2 will get cancelled. So, what is the unknown value here? These two are fixed, this is a variable, always the unknown will be this point. Okay. So, R4 you have to find out. See, where is R4? You have R4 here. So, R4 unknown resistance, R4 is equal to R2 into R3 divided by R1. So, this is the formula which we make use to calculate the unknown value of resistors. So, R2 into R3. R2 into R3 divided by the opposite branch, okay, R1. So, this is how accurately by adjusting this R3 value, we are going to calculate the unknown resistance. Have you followed how we are going to find out the unknown resistance? That is measuring the value of the unknown resistance using a DC Wheatstone. Now, take down this problem and directly substitute and now this property which we studied was for a balanced Wheatstones bridge. Now, when the Wheatstones bridge is unbalanced, okay, we find out a term known as sensitivity. Means if the Wheatstones bridge is an unbalanced condition, what happens? There will be a deflection that is present within the galvanometer. Okay, so this deflection, the amount of deflection that is found in the galvanometer is nothing but the sensitivity. Okay, so we can also define sensitivity as Okay, what is the amount of deflection per unit current? For the current that is being flowing into the circuit, what is the amount of the deflection that is found within the galvanometer? That part is known as the sensitivity of the galvanometer or sensitivity of a Wheatstones bridge. Okay. So, in general, total deflection, what is the total deflection found in the galvanometer? Total deflection D is nothing but the sensitivity into the current flowing. So, this sensitivity or the deflection can be in terms of the angles or it can be in terms of millimeters. So, you can have the unit depending on what type of galvanometer reading is present on the scale. If it is in radians or if it is in degree or if it is in millimeter. So, you can have the units as millimeter per microampere or you can have degree per microampere or you can have radians per microampere. So, depending on what type of scale is being used within the galvanometer, we can have different units for the total deflection of the galvanometer. Okay, so this part sensitivity we are going to speak when the Wheatstones bridge is an unbalanced condition. Okay, not only with the sensitivity, now when the Wheatstones bridge is unbalanced, we cannot directly find out what is the actual value. Okay, we cannot directly solve the circuit. So, we would have to make use of the Thevenin's theorem. Okay, Thevenin's theorem, what does it state? Whenever we want to find out the Thevenin voltage, then we are going to short circuit and we are going to consider it as a single resistance. We are going to solve the entire circuit. So, making use of that concept, now we will see how we can find out the unknown value of resistors for a unbalanced Wheatstones bridge. So, now let us see how we are going to find out the unbalanced Wheatstone bridge, how we are going to analyze the unbalanced Wheatstone bridge. Now, what is our interest? We know that when the galvanometer shows a zero deflection, the bridges are balanced. Okay. So, we know that it is an unbalanced bridge. So, what is our interest? We need to find out the current in the galvanometer. That is our interest. Okay. So, what we are going to do? We are going to make it a open circuit. Remove the galvanometer and call the points as A and B. Okay. Why? Because we are interested in finding out what is the current in the galvanometer. If we come to know that the galvanometer current is somewhat which is not equal to 0, then we can say it is a unbalanced bridge. Okay. So, when we are having a open circuit voltage, what happens? We have two different potential points. One is because of R1 and R3 influenced by V, and the other one is R2 and R4 that is also influenced by V, but which follows a different path. Okay. So, we will also mention the currents. Determining the voltages at point A and point B, we can get the Thevenin's equivalent circuit. Okay. As I said, we are going to make use of Thevenin's equivalent circuit for an unbalanced Wheatstones bridge. We are going to make use of that. First, we will find out the voltage developed across the potential A. Okay. What is the voltage developed? This is the total voltage V into R3 divided by R1 plus R3, voltage developed across A. Similarly, what is the potential developed across B? V into R4 divided by R1 plus R2 plus R4. Thevenin's equivalent, how do we find? Thevenin's equivalent is nothing but VA minus VB. So, VA is VR3 by R1 plus R3 minus V into R4 divided by R2 plus R4. Therefore, we can also write the Thevenin voltage as V is common R3 minus R4 divided R3 by R1 plus R3 and R4 divided by R2 plus R4. This is equivalent to V Thevenin's. So, we know that if we replace by an impedance, then we can find out what is the value. So, the equivalent circuit for this Thevenin's equivalent, whatever we have got here, this V can be replaced by its internal source Rs, let us say, which is equal to 0. Very small internal resistance is present with the source. Okay. So, let us assume that to be equal to 0. Now, what will happen? Now, you can see R1 is in parallel with R3 plus R2 is in parallel with R4. Now, can we write out the Thevenin's equivalent? V Thevenin is found out. Now, we have to find out R Thevenin. Okay. So, what will be the value of R Thevenin now? So, this is in parallel. So, R Thevenin, we can write it as R1 into R3 divided by R1 plus R3 plus R2 into R4 divided by R2 plus R4. Okay, so V Thevenin and R Thevenin is found out. So, can we find out the current now? The equivalent circuit can also be replaced as V Thevenin, R Thevenin. And what are we interested in? We are interested in finding out what is the current that is flowing between these two terminals A and B. So, in order to find out the terminals A and B, what is the potential that is developed here, we are going to follow the Thevenin's equivalent circuit method, in which we are short circuiting this, finding out the separate potentials at point A and point B, then point A, B will be equal to the V Thevenin voltage, find it out. Similarly, when you replace this voltage source, you should find out V Thevenin and R Thevenin. So, you will be replacing this voltage by a small internal resistance. Here in this case, approximately it is going to be equal to 0. So, making use of that, what we are going to do? Take the parallel combination. R1 is in parallel with R3, R2 is in parallel with R4, write the equivalent equations, you will get a R Thevenin. So, V Thevenin and R Thevenin represented in this way, Thevenin's equivalent circuit. Now, once we are going to get this value, what we are going to find out? The current flowing through this point or through the galvanometer. Okay, so the current through the galvanometer is our interest. So, Ig is equal to V Thevenin divided by the Thevenin's equivalent plus, when you have a galvanometer connected here, the galvanometer will also be having a small resistance. So, we are going to consider that. Okay. Like this, you are going to find out what is the current through the galvanometer. That was our interest. In order to find out or in order to analyze the unbalanced Wheatstones bridge, we found out the galvanometer current by making use of Thevenin equivalent. Okay, using this circuit, the potentials across A and B was found out. When you are connecting a galvanometer, even that has a small resistance, internal resistance, or we can also say galvanometer resistance. So, that gets added up here. So, by making use of this galvanometer current, you can vary it by making use of R3. So, by varying say the Thevenin's resistance, we can obtain the galvanometer current and make it to a balanced condition. This is the analysis of a unbalanced Wheatstones bridge. I hope you have understood it. Okay. An unbalanced Wheatstones bridge is shown in figure. Calculate the current through the galvanometer. The specifications are already given. Use the specifications and then find out. Whenever they say unbalanced, it has to flash in our minds that we have to calculate the Thevenin's equivalent. Okay. So, first we have to calculate the Thevenin voltage, Thevenin resistance, then find out the galvanometer current. Okay. The previous derivations, whatever we use, the last formulas which we have done, use the same formulas. Okay. V Thevenin will be equal to, what is the value? So, whatever we did was VA minus VB, or you can take VB minus VA, any choice. Okay, take the magnitude of the value. Now, let us take R4 divided by R2 plus R4, VB minus R1 divided by R3 divided by R1 plus R3 into V. 4 divided by R2 plus R4 minus R3. This is, we have taken VB minus VA. You can take VA minus VB or VB minus VA. If you are getting the negative value, take the magnitude of that. Okay. Now substitute the values. V is equal to 6 volts. R4, what is the value of R4? 10 kilo ohm divided by R2 plus R4, 2.5 plus 10 kilo ohm minus R3 value is 3.5 kilo ohm. So, 3.5 kilo ohm divided by 3.5 plus 1 kilo ohm. Okay. Simplify this and tell me what is the Vennens equivalent. Somewhere around 0.132 volts, are you getting the value of Thevenin? Okay. Similarly, can we find out R Thevenin? So, what is the formula for R Thevenin? Here let me write R Thevenin is equal to R1 into R3 divided by R1 plus R3 plus R2 into R4 divided by R2 plus R4. R to all the values and tell what is the R Thevenin equivalent. Okay, carefully you must do the calculation. Around 2.77 kilo ohms you are getting. 2.77, what is the point after the decimal point? You can take 2 digits or 3 digits, it is your choice. Thevenin and R Thevenin are found out. So, can we write it like this? Thevenin is connected with respect to R Thevenin, and you have a galvanometer AB terminals. Galvanometer is connected here with a resistance of 300 ohm. Can we write like this? Now, Thevenin and R Thevenin you have calculated. Can you find out the gate now? Gate current. So, Ig is equal to Thevenin divided by R Thevenin plus Rg. So, find out what is the value. 0.132, R Thevenin is 2.77 kilo plus 300 ohm. What is the galvanometer current you are going to get? Value 42.88 microamperes. See whether you are getting the same answer. 42.8 microamperes is the current that is flowing through the galvanometer. Followed how to solve. This is for an unbalanced bridge. For a balanced bridge, directly you apply R4 is equal to R1 into R3 divided by R2. Okay, the formula which we have derived before. Followed how to solve the problem. Next, if this is an unbalanced Wheatstones bridge, okay, when it is completely unbalanced. If it is slightly unbalanced, some extra term you have, then how can we analyze the Wheatstones bridge? That is what we are going to see now. Which means now out of the 4 arms that is present in a Wheatstones bridge, if 3 arms are having the same value of resistor and only the 4th arm somewhere around 5% there is some difference in the value of the resistor, then how can we accurately determine the unknown resistance value is by obtaining the method or by understanding the concept of slightly unbalanced bridge. So, in case of a slightly unbalanced bridge, a Wheatstones bridge, here all the 3 arms are going to have the same value of resistance. Okay. Let us say R, all the 3 arms are having the value same resistance, whereas only this is having some small change, say less than 5% change. Okay, then how we are going to calculate or how we are going to derive at the analysis of a slightly unbalanced Wheatstones bridge. This is nothing but the Thevenin's voltage. Since it is unbalanced, we cannot take directly the balanced condition. So, we are going with the. So, now coming back to the analysis again. Now, at point A and point B if we consider. So, what will be the voltage across point A now? Point A will be equal to V divided by 2R. So, here coming to the point we can take the total voltage into the resistance, addition of 2 resistance. Okay, so here can we write it as V by 2. Okay, similarly at the point VB, V into R plus delta R, V into R plus delta R, small change divided by the sum of the resistors that is the voltage divider rule we are applying here. So R plus delta R. So can we write it like this, V into R plus delta R by 2R plus delta R. Okay. So this is the potential across VA, VB. Now to find out VThevenin, what we should do? VA minus VB or VB minus. So since, see now, we have to do for Thevenin's equivalent VA minus VB or VB minus VA. Since this is a bigger term, what we will do? We will take VB minus VA. Okay, so V is common here. R plus delta R divided by 2R plus delta R minus V is taken common, so 1 by 2. Okay, so can we take the common now? Can we take the LCM now? So what we are going to do? 2 into 2R plus delta R. Cross multiply. So 2R plus 2 delta R minus this into this 2R minus delta R. Okay, into V. Understood? Now my plus 2R minus 2R will get cancelled. You have 2 delta R minus delta R, you will get delta R divided by 4R plus 2 delta R. This will be your V Thevenin's equivalent. Followed, you can either take VB minus VBA or VA minus VB, substitute and get the V Thevenin's equivalent. Since it is unbalanced, we have to follow the same procedure of finding out the Thevenin's voltage, Thevenin's resistance, then finding out the current. See, in the denominator, if it is 5% less, means a very small value. So you observe here in the denominator, if you are going to get small value of delta, 4 times the kilo ohm plus small change, 5% change means a very small amount. Can we neglect this term here? So can we write it as delta R divided by 4R is the Thevenin's equivalent? Yes. Okay. So what about V? V into delta R divided by 4R plus 2 delta R. So here also V into delta R divided by 4R. So this is the Thevenin's equivalent. Now once we get the Thevenin's equivalent, we have to find the R Thevenin also. R1 by R is in parallel with this. Okay, so R into R plus R into R divided by 2R plus R into R plus delta R divided by R plus delta R. This is the resistance, Thevenin's equivalent. Now R and R will get cancelled, so it will be R by 2 plus R into R plus delta R divided by 2R plus delta R. See, whenever you don't have an addition with respect to the small, you can keep it directly the change. But here when you are adding with the quantity higher value in kilo ohms, then what will happen? This delta R will be neglected. So both the numerator as well as the denominator, you can neglect this delta R. So you will get R by 2 plus R into R divided by 2R means, can you get R by 2? R and R will get cancelled. So the remaining is R by 2. So the R Thevenin's equivalent will be equal to the resistance R. Okay, now we have got V Thevenin and R Thevenin, and V Thevenin is available. So V Thevenin and R Thevenin for a slightly unbalanced bridge. This is, let us say, the points A and B. For a slightly unbalanced bridge, this is how we are going to analyze. Take the V Thevenin. Only at the voltage you have an effect of the small variation in resistance. Apart from that, the Thevenin's equivalent for a slightly higher value will be the same. Okay, so this is about the Wheatstones Bridge, a balanced Wheatstones Bridge, unbalanced Wheatstones Bridge and a slightly unbalanced Wheatstones Bridge. I hope you have understood the difference between all the three circuits. Now, can we solve a problem based on this slightly unbalanced bridge? Okay, take down the balanced Wheatstones Bridge, which states that Given a center 0, 200 microampere, this is the range of the galvanometer, okay, movement having an internal resistance. So, the galvanometer resistance is given as 125 ohm. Calculate the current through the galvanometer. Okay, they have given that it is a slightly unbalanced bridge. The figure is given. So, see, when you see the figure itself, 700, 700, 735, 700. Okay, so there is a 5% change when compared with the other 3 resistors. So, what we are going to have here, a 5% change is available. So, it is a slightly unbalanced bridge. So, can we write the Vennens equivalent now? Vennens equivalent is equal to V into delta R divided by V into delta R divided by 4R. So, substitute the value 10 volt and delta R. See, you can see the change here, R plus delta R. Can you write 700 plus 35? This 700 plus 35. So, this R plus delta R value is equal to 35 divided by 4 into 700. So, this gives the value of the Vennens equivalent 0.125 volts. Okay. Now, compared to the R Thevenin is equal to R, that is equal to 700 ohms. Once you get V Thevenin and R Thevenin, can you find out the galvanometer current? The galvanometer current is equal to V Thevenin divided by R Thevenin plus the resistance, small resistance available in the galvanometer. So, Thevenin's voltage what you have got? 0.125 divided by R Thevenin is 700 plus the galvanometer resistance. See in the problem, 125 ohm is the resistance across the galvanometer. So, 125. Substitute and find out the current through the galvanometer. So, this is how we solve the problems related. 151.5 microamps is the value. Understood? So, this is how we solve the problem on slightly unbalanced Wheatstones bridge.